Okay, it is week 13. On Thursday, we have exam 2. Let me remind you, assignment 13, I'll go homework 13, is review. I would work it before you take the exam. Lab 13 is, I should look at this right. Lab 13 is a capacitor review lab. So this will not be on the exam. Here's why we're doing this, so I'll just go ahead and look ahead. Week 14 and week 15 are a bit of a shift in gears. We covered inductors and capacitors for DC circuits. So if you recall, last semester we did a week on inductors and capacitors. We'll go back and we'll do pretty much the same sort of thing, just a little deeper and a little more. And we'll have, I think, 3 total labs that cover those that have. We didn't get to do an inductor lab last semester, so we'll do one now. So it works out nicely. We have exam this week, and then we have 2 weeks of something different. Okay, so looking forward to that. Let me check. Project 1 should have been done a while ago. If you haven't done it, get it into me. Bring it in, demonstrate it. We do have a project 2 that's out there for this class. Okay, so we got time to do it the last few weeks, but don't neglect those. Those are both 50 points, so together we're 100 points. Okay. All right, that's on logistics. Now, if you look in this week's material on Blackboard, I have both the homework and the assignment, and I have a review sheet that has a list of. I've done those before. I think I've tried to do them for most exams, but I don't know if I've gotten all the classes yet. But they will have a list of terms at the beginning. If you see a term you don't know, go look it up. Like, you should recognize those and have an understanding of what they are, even if you couldn't write down a detailed definition. If you write down a detailed definition in your own words, that's better. But at least you don't get to the exam and go, well, I've never heard of this before. And then there's a list of principles below, and concepts and things you have to build work. So let's just talk briefly about what we've covered since exam 1. So going into exam 1, we did the Kirchhoff's laws. I'm going to write them down because they're the foundation of everything we do. So Kirchhoff's, we either see them as current law and usually loop law or voltage law. I write CVL. All right. The current law says all the current into the junction equals the current out of the junction. And the voltage law says all the voltages that go around a complete loop on the circuit sum to 0. Or all the voltage in equals all the voltage out. Either way you want to look at it. All the voltage rises equals drops. All right, these 2 laws, after Ohm's law, are the most foundational thing in electronics because they cover everything. Everything in DC, and we get to AC, and we talk semiconductors, they still count. Okay, so we should have those down. Off of those, we build these techniques up to make the mathematics easier. So we can work that problem we did with 2 sources. And we've done a bunch of these now. I'll go ahead and redraw just a source, a resistor, a resistor. So these are what we used to develop them. And these are, in some ways, the most simple version of these, but we write down each one. So one of them is if we did these, we would end up with an equation for the loop, and for the junction with currents going in and out. It'd give us 3 equations and 3 unknowns. Now, after this, we did mesh currents. Mesh currents, we said I'm going to recognize, using this fact I know what this law is for the node, I'm just going to skip doing that equation and instead realize, hey, if I have a current here, this current's I1, and if I have a current here, I can call this one I2. I1 flows through this, I2 flows through this, I1 plus I2 flows through that. So I get two equations with two unknowns immediately, but this is just recognizing and using this, and then coming up with a slightly simpler mathematical way of handling it. Of course, now that we have this, what we'll actually do is we'll do problems that give us 3 mesh currents that are bigger, that have given us like 4 or 5, well, Kirchhoff's laws. So that's my mesh current. After that, we did nodal voltage. Nodal voltage builds, it's all about voltages, except for it's really all about currents. It's really about the node. And it says, I can find the voltage right here to some other spot, and we would normally have this ground. So if you're like a multi-sim, that's how we'll do all its voltages by default. Those voltages are always from there to wherever you define as ground. In fact, you probably have found if you've used multi-sim, but if you don't put a ground in, you get funky voltages on things because it just kind of makes one up. It's like, I don't know what ground is. So what I recognize now, I can draw this as the current that comes in here, and that current is going to be this source voltage, whatever it is. A lot of times you label it as E, so I'll do that just to make it simple. The voltage drop between here and here over this resistor. And I could draw the voltage here, or the current here, which is also the voltage drop over that resistor. And I can draw the current here either going away or going towards it. It doesn't matter. It depends which side of the equation it's on. If I draw it going away, then I would say that current is this voltage minus ground over R2. So I could write the equation out as all the current in equals all the current out. I could have also written it all as all currents gone in. Here I would have been 0 minus V. So you'd get minus V over R2 and be on the other side of the equation. It'd work out. At this point, all I really want to do to solve these is find a common denominator I can multiply through by, or something that makes these nice, simple decimals I can plug into my calculator and solve for V. So for this particular problem, once I get to nodal voltages, I actually have one equation and one unknown to solve everything. If I ask you to set up the equations and solve either of those, are we good?
I think so.
I would review them before the test on Thursday. Okay, and on Thursday, I might just give you a problem and say, solve the voltages and currents, and let you do it however you would like. It's fair game for me to go set up, and I might do something like just set up the mesh currents for this equation. I can have you solve it or solve it with mesh currents. I've done before one where it's like, solve this equation, part A, with mesh currents, part B with nodal voltages. If I do that, feel free to check them against each other because you gotta get the same answer either way. Okay, the next one was superposition. Superposition says I can remove a source, replace it with a short if it's a voltage source, and then just solve the entire equation, everything for voltages and currents. And then I can remove the other source and solve everything for voltages and currents. And I can just add them all together. So, if I do this, I'm down to just a simple little series parallel circuit, which we did the first week of the semester. The only caveat I will warn you on this one is watch your directions. because it's easy to end up with one source pushing current this way and the other source pushing current that way. And they add, but that means you're going to get the difference because they're pushing opposite directions. So watch your directions on everything. You should be good, but just be careful. That's the biggest thing people get caught up with. But yeah, superposition, very powerful. If I have a current source, I'll start with current 1. When I remove it, I leave it open. Basically, if you know what you do with the voltage source, you always do the exact opposite with the current source. There is Millman's theorem in there. I didn't end up covering it. I will not put anything specific to it on the test. You had to do a homework problem or two just to read it and do it, but it builds towards superposition, so that's kind of Thevenin, Norton. So Thevenin. Okay, I guess I should have left my whole circuit on here. When we work this one in class, we assume this is the load. So what we did was we removed the load and just call this open R load. The voltage here is the Thevenin voltage, and the total resistance is just the total resistance in the circuit once we remove our two sources, right? From the perspective of this. So if I remove these, and again, replace them with shorts, then if I'm going from here to here, that resistor is tied to both sides of this resistor. So those two resistors would be in parallel, right? From the perspective of R. All right. So when I'm all done, I should end up with the Thevenin voltage and that Thevenin resistance. And here's where my load will go.
What did you do to get Thevenin voltage again? You
You just find the voltage between here and here.
Yeah, okay.
Just remove that resistor that you want to, that's your load, and then find the voltage between the 2 points on it. Okay, and if you want Norton,
Oh wait, that's Norton?
yeah.
Oh.
So Norton is, it's going to be the exact same. I'm going to write it this way because it's the exact same voltage. Our resistance is Thevenin resistance. And this current is the current that will come out of here. Yeah. So this current if you have the Thevenin value, you can just do that. Norton and Thevenin are really the same thing, except for do you want a voltage source or do you want a current source? I would say most of the time for practical real-world circuits that we're looking at an entire circuit, we're going to be thinking voltage source. However, there are a lot of cases where this comes up when we talk about things like transistors and such and how they're a current amplifier, so they're really a current source. So how do we model them? So a lot of the current sources come in modeling. But even over here, our power supplies, I can set a maximum voltage. I can turn the current up. I think they go up to like 5 amps or something like that. Don't try that through my boards. but they'll easily get to an amp or two because I've used them before for like physics labs. We're running an amp or two through a wire to measure Ohm's law through a wire and measure the voltage between the ends and the current flowing through it. And then go back and try to figure out the material the wire is made of. Speaking of which, resistance, resistivity. Look at that segue. Before we get out of here with these, tied directly to these was maximum power transfer. It's an important concept. So we can calculate my power delivered to the load. So what's going to happen? As the load resistor, if it starts really small and gets bigger, as it gets bigger and bigger and bigger, this is a series set of resistors, right? So as this gets bigger and bigger and bigger, the current will go down, but the voltage across this will go up. Right? The voltage across this resistance, this is the voltage divider, right? The voltage across here will be proportional to this resistor, actually equal to this resistor, divided by the total resistance times the voltage. So as this resistor gets bigger, current will go down, but its actual voltage will go up. And you can look and go, you know, power is current times voltage. So hold it, one's going down, the other's going up. Power is equal to current squared times resistance. So as current goes down, maybe my power goes down, but the voltage squared goes up, so my power goes up. If you try to reason your way to it, you probably get a little bit of a reason loop. That's why we worked through the one in class. We're like, okay, let's try this. Sure enough, the power goes up, and then it goes down. So the maximum power on the load, if you recall, was, if this is the resistance, was when the load resistance equals the Thevenin resistance. At that point, this power is half the power in. That's the best you can ever do. It's half power delivery. The other half is on the resistor. All right, so yeah, so it's an important concept, and since we proved all that, you do know, hey, if I ask you, what load would be the maximum power, you can go, oh, well, that's just when it's equal to Thevenin resistance. Or I've asked before, what's the maximum power I can deliver to the load? And you would go, well, that's when the resistor is equal to the Thevenin resistor, and I'll figure out the power of that resistance. If you aren't sure in your middle exam and don't remember all this, A, you could have written this all down in your equation sheet. And B, you can actually just try a couple to remind yourself, oh, let's try, you know, this half of this equal to this, and this double that, and just see how does it go as the resistor goes past this, which is a general principle you can do on anything, right? You can always go, hey, I don't remember how this works. You know, I have one, let's pick an easy number. I have 1 kilo ohm input resistor. So I'm just going to try, you know, 500, not a standard one, but 510, another 1 kilo ohm and a 2.2 kilo ohm, and just see how it changes. And then I'll have an idea of what happens as the resistor goes past being equal. So you can always do that stuff. You can always just put numbers in, try it real quick, and see how it works out for you. Okay. Resistivity. Resistance is the resistivity times the length of the resistor over the area. You need to know that equation. You need to know how to use it. You need to understand area if it's given to you in C-mils. You also need to recognize if I give you the diameter or the radius, you can do pi r squared. You should probably know how to get the area of the circle by now. Write it down. Don't forget, it's common to give you the diameter, which means you got to divide it by 2 to get the radius, and then do your calculations. I will not expect you to write down or memorize those tables. I will expect that I could give you numbers out of those tables, or give you an abbreviated set of values in those tables. You can pull them out and use them in a problem. Questions on this? Does it all seem familiar now that we've done it? Yeah. I'm hoping it doesn't seem too bad. I mean, it no doubt, these are calculation problems. You're going to sit there and calculate. Go through them. So bring your calculator and bring a writing utensil or two, in case you like run out of ink with your first pen or whatever. Or pencil. Use a pencil. They're better. And by the way, if you make a big mistake somewhere, you can kind of scratch things out and grab a blank sheet of paper and just staple it on the back instead of trying to write all around. Almost certainly. I'm going to try to find problems where I test your ability to do each of these. So it's hard really, because I'd like to go, hey, here's a mesh current problem, here's a nodal voltage problem, here's superposition, here's Thevenin, here's Norton, here's maximum power transfer, here's a resistivity, and then pretty soon I've got like 10 problems that each take 15 minutes. So I can't do that. So I'll write out that stuff and I'm going to cut it down. But I guarantee you'll see these. You should probably expect to see a problem that covers these. You should probably see a problem or a couple of problems that are hitting these and force you to do these. Since these tend to work on different types of problems, what we'll do is try to find 2 or 3 that you go, oh yeah, the mesh current. Make sure you go back. A common problem for exams, students. A Wien bridge type problem. Can't really do that very easily until we do these, but you remember I asked a bunch of those in the homework, didn't I?
Yeah.
And really. Three equations, 3 unknowns, a bit of algebra, but 3 mesh currents do it for you. Just keep your current direction, straight. You should be good. Solve and end up with 3 currents and solve whatever voltage you need. If I ask you for the voltage for a single resistor, you find the current through it. Just use it and find it. Move on. You're going to find everything. Anything else? I said review the homework. Look back when you did the calculations. All these labs had a do this calculation first thing going, so do that. Otherwise, I'm going to say go have a good week working on stuff. I need to pull back up what project number 2 is in this class. Oh, it's the SMD. Never mind. That's this class. So we're good. You got both projects. It's the other class that needs the second set of projects written. So they'll be done shortly. Let me shut the camera off.